You are too young for dad jokes. All right, so if you would, which most of you are, but I had the recording paused, so I just restarted it. We are taking the quiz at the bottom of the bonded module. It says bonded, determining bond types and properties. Please use your periodic tables. I'll turn the light on. I can see many people struggling to read those little numbers. Use your periodic table, find the differences, then look to the right side, and all those answers should be there for you. No, that's in chemistry A. Yeah, so hit your dashboard. Yeah, that'll work too. Then not that far down. Right there. Yep. Yep. Okay, take a minute. I'll go ahead and pause. If you miss any, I invite you to leave. All right, I forgot just a couple minutes there, but we're doing pretty good. Carbon and fluoride combined, they form a polar substance. So you don't even have to do math. It tells you it's polar, so then you just go to the periodic table. So will the substance dissolve in water, hexane, both, or neither? It is just water. Be careful. It's not a yes or no question. Like these people, they're not wrong. They just didn't read the question correctly because it does dissolve in water, but not hexane, both, and neither. So just read it careful. So really, you would have had it right. You just need to read a little more careful. Ooh, that one's really low. Will a substance have a relatively high, medium, or low melting and boiling point? So if you look at your periodic table, this one's kind of ugly. It's just a picture of someone's from last year. If you go to polar, you will notice that it has medium, melting, and boiling point. Okay, it should be written right there. So it's that time of day, time of week when I get all my fantasy alerts that yes, I still suck at fantasy football. What a year it's been. But not as bad as Patterson or Savage. All right, that looks good. That one looks no good. Well, hello, my friend. What a cute note. Oh, is your mom okay? All right, well, I'm sorry. That's a rough start to a day. Oh man. I fell down the stairs with Derek in my arms when I was young, when he was a baby. And it was either him or me. So so I landed on him. He was nice and chubby. I don't know. No, I went down hard and just kind of held him up. And it hurt my neck for like 3 weeks the way I landed. And he just laughed. Um, anyway, okay. It says, will the substance conduct in solution? 56%. Again, be careful. All these answers are on here. If you look at conductivity, it says none. So the answer is no. Polar things don't conduct in a solution. Okay, we won't spend a ton of time, but hopefully these were okay. I mean, our average was 86%. I'm not going to complain too much about that. Some of you need to practice more. I did notice 3 kids took this without their periodic tables. That's fine, but why? Every answer and the process is on there. So please make sure and use the resources I provide for you. All right, the rest of the daily plan, if you logged in and read it, it would be right here. Once again, this little thing in red, the last time I taught this lecture was on April 13th or March 13th, 2020. So if we don't have school tomorrow, that's my fault. And I apologize. But I'm pretty sure we will. I only know as of right now, we only have 5 cases. So I think we're doing fine. Only one of them's even been in school. So that 2-week break did us some good. Now my neighborhood got destroyed, but school's fine. Yeah, Curtis, it's around our neighborhood bad. So don't breathe outside. They do? Yeah, it's bonkers how many houses on my street have it, but I don't. Okay, so you don't need to do this. This is practice from last year, and we just took a quiz on it. So let's go ahead and turn to page number 7, if you would. And have your periodic table out. Let's do something real quick in case, well, not in case. You probably don't have it, and we're going to use it as we go through today. So this is just someone's day left last year. I just took a quick picture of it and dropped it on here. It might look similar, it might look different than yours. It's whatever. But what I would like you to do now, I would like you to add these charges right up here. You may already have written them down here, but whatever. So above H, I want you to put a +1. Above BE, I want you to put a +2, +3, plus or -4. That one's tricky. -3, -2, -1. Yep, noble gases don't have anything. All right. So what these things are, and if you want to label them somewhere, I know that this thing's really crowded. You don't have to, but if you feel like it, you can. These things are called their ionic charge. What the? There's a C right here, Tom. So today we're going to talk about ionic bonds. We will talk about their charges that they form in compounds. And they're really nice. Family 1 forms a +1. Family 2, a +2. Family 3, a +3. Family 4 is a plus or -4. And then we have 5's a -3, O's a -2, F's a -1. Why do you think these make negative charges and these make positive charges? Tell your partner real fast. Your best guess. Why do these form negatives and these over here form positives? No. No. Could anyone finish this sentence right here? Losers. Thank you for coming, even if it was late. Metals are losers. What are they losing? They're electrons. What are the charge? What is the charge of an electron? It's negative. So it's a little tricky, but if you lose negative, you're going to form positive things. You all right with that? Okay, so non-metals, things reverse. What are they doing? They gain electrons. So I know it's kind of weird again, but if you gain something that's negative, you become negative, right? So you find the perfect boy or girl to have as a boyfriend or girlfriend, but then it turns out they're super negative. Well, you become negative. It's just a fact of life, kids. Choose wisely. Those decisions make a huge difference. Okay, so we will learn more about these, but when we talk about ions and their charges, remember 1, 2, 3, plus or minus 4, because they're trying to obtain an octet, right? So 4 could lose or could gain. And then we get -3, -2, -1. All right, here we go. Ionic bonds. So page 7, there's not a ton of notes, but I'm going to talk a lot because that's what I get paid to do. So ionic bonds are bonds with differences in electronegativity of 1.7 or greater. What a good game to play. All right. Now, will you tell your partner one other place that you could find that definition, that ionic bonds are 1.7 or greater. Point to it if you would. Uh-oh. David, all right, he knows. It's on your periodic table, right? Can I borrow? It's just right there. Ionic bonds. One atom is a metal or the other is a non-metal, or has a different greater than 1.7. So it's on your periodic table. Yes.
What about, so it says or is a metal. What about the metals right over here?
Those are good.
Well, like, because they're a plus or minus 4, so they could become a negative.
So that's tricky. These will be your minuses. These will be your pluses. Based on where they are in their staircase.
Okay, that makes sense.
All right. So if we have a great difference in electronegativity, we have an ionic bond. That's because they lose and gain, forming ions, and that gives us an ionic bond. Okay, ionic bonds do not share electrons. You absolutely have to know ionic bonds do not share. Rather, one element gives up electrons and the other takes them. All right, so it's like you gave your friend a Mountain Dew for Christmas. You don't expect them to then share that Mountain Dew with you. Like, I guess they could, depends on how good a friend you are. But, all right, it was given from A, it's given to B. There's no sharing, it's given. All right, next. In ionic bonds, electrons are transferred between atoms. They literally move. Now, probably not in a U-Haul van, but once again, we have Na, we have Cl. Na has an extra electron, chlorine is missing one. The electron literally moves from the sodium atom to the chlorine atom. Now, Kennedy was over there playing a game on her phone. She might still be. Her phone is actually being powered by this exact process right here. Now, it's not Na and Cl, it's a lithium ion battery. It's called a lithium ion because it's moving its electron over to whatever is on the right side. I don't know. It doesn't really matter, but we call it the anode. The electron has to physically transfer, and what we do is we use its flow from here to there to power electrical devices. So any battery is just taking advantage of an ionic bond being formed. Now, Kennedy, can you recharge your phone? Yeah, it's not a single-use battery, or that'd be a really expensive phone. Every day you'd have to buy a new one. So this happens naturally. So nature causes the electron to transfer from sodium to chlorine. But let's pretend now, I'm not much of an artist, but this is my plug. I plug it into the wall, and now I produce electricity that will force the electron to go to sodium. It doesn't want to be there, but if I plug it into the wall and put 120 volts to repel it, I can make it happen. But the moment I unplug it, it goes back to going this way. So we can do this over and over and over. So a battery is taking advantage of the formation of ionic bonds when the electrons move from one place to another. All right, ionic bonds are usually between a metal atom and a non-metal atom. In this class, pretty much, they will always be between a metal and a non-metal. There's like one exception, and we'll talk about it later, but by the time we talk about it, you won't even have thought about it, so whatever. If you ever see a compound start with a metal, it will always be ionic. So if it was like AuCl3, gold, that's a metal, that means it's ionic. If it's NaCl, sodium, metal, that's ionic. Aluminum fluoride, aluminum's a metal, ionic bond. Now, how do we know if they're metals? Remember this awesome chart, staircase, metals, nons. Now, hydrogen is not a metal, so just be careful up there. Okay, it is a non-metal. But any of these, if you see a compound that starts with any metal, it will always be an ionic bond. Okay. Now, I've printed an old version. This is supposed to be on your page, but I must have printed the previous version that did not. So you don't have to write this whole sentence, but this is a matching term. So metal atoms always want to give electrons. That's why we call them losers. Then once again, this is supposed to be on your page. When metal atoms lose electrons, they form a positive ion called a cation. So the matching term is cation, and you have to match it to a positive ion. That's the matching. So you don't have to have the sentence memorized. You just have to know a cation is a positively charged ion. Now, you can sort of remember that if you think about how the sign of the charge is in the name. So you have a cat with a positive in the middle of it, a cation. There's the charge, okay? Cation is always positive, and that comes from the metal. We have to know that metals form cations. We don't use that term a ton in this class. You'll use it a little bit more often in MAP, actually. But so the positive is the cation. If you ever watch a YouTube video and it is from like Europe, they call it a cation, but whatever, same thing. All right, non-metal atoms generally want to take electrons. When non-metal atoms gain electrons, they form a negative ion called an anion. All right, so tie these together. Non-metals form negative ions, and we call those anions. It would be nice if there was a negative sign in the middle of the word anion, but there really isn't, unless you put your eye sideways. But that just looks stupid. You're welcome for my geniusness. Okay, anions, negatives come from non-metals. So we know metals lose, we know non-metals take, then metals form cations, non-metals form anions, and then we have the ions that will come together. Ionic compounds or molecules are electrically neutral in that the number of plus equals the number of minus charges. Okay, so write that in and then I'll go to the next page. This slide is going to help us to be able to determine the formula of an ionic compound using the periodic table. It's really simple, and we'll do that for the next 10 minutes. So what it means that they are electrically neutral is that everything in nature has to be neutral. So I've drawn Na and Cl a lot as my example here. So looking at my periodic table, Na will have a +1 ionic charge. We okay with that from what we labeled? And it makes sense because Na had one dot or one valence electron that it wants to lose. It will give that electron away because chlorine, if you remember, has 7. 1, 2, sorry, oh, that's just ugly. 1, 2, 3, 4, 5, 6, 7. And I just left that one blank there because my arrow already pointed to that area. So sodium will donate this one to chlorine right here. If I look up here, sodium is a +1 because it lost this one. Chlorine, I look at it and it is a -1. This slide is saying that these numbers up top will always add to 0. If they don't, then the compound is not correctly written. You kind of all right with that idea? All right, so that works for NaCl, but let's talk about when Na and oxygen combine. So we know we have Na with 1 dot, but oxygen has how many? Tell your partner, how many dots? 6. That was very unconvincing, but it's 6. So I'm going to put 1, 2, 3, 4, 5, 6. All right, now sodium and oxygen can form a compound. Sodium will give one of its electrons to oxygen, and I'm going to put it here just to make it look better. So now sodium has lost, so it becomes a +1. Is oxygen happy? No. So tell your partner what it needs. What do you mean, Jared? It needs another electron, and where can it get it? All right, perfect. So I need a second Na. I can't take 2 of them from 1 Na. That's not how it works, but I can take 1 from 2 NAs. And now oxygen, if you look right here, it's a -2. That makes sense because it took 2 electrons. Each sodium gave away 1. So this formula would be 2 NAs to every 1 O. Kind of okay with that? All right, that would be electrically neutral. Stick with me, I can definitely sense I'm losing you. These numbers up top have to add to 0. It may not look like they do, but if we look and we say, hey, I have 2 times +1, that's really a +2, correct? And then 1 times -2 is just -2. These added together definitely make 0. Okay, so when they are electrically neutral, these formulas and these charges, when we do the math, will always, always, always equal 0. And that's how we can find the formula of any ionic compound just looking at the periodic table. So let's do one more the hard way, and then I'll teach you the easy way. So if I had calcium, and it was going to bond with nitrogen. Calcium has 2 dots to give. Nitrogen needs 3. So this is a little tricky. Will you, oh, see what? Ca 3 and 2. How did you figure that out so fast? What math? Okay. Then bam. Makes sense? All right, he's 100% right. I don't know about the bam part. Okay. Oh, that's good feedback. All right. So what we can do here, I just wanted to come over here and just, get this side of the room involved also. Is that all right, Odessa? If we look, these have to equal each other at some point, right? So they have to add to 0. So in order for a +2 and a -3 to add to 0, we need to make them both a number that talks to each other. We need 3 of the 2's, that makes a +6. We need 2 of the -3's, which makes a -6. We add them and we get 0. So dot wise, we would look here and we would need two CAs and three CAs and we need two Ns. And that will balance everything out. Each one of these three will donate one to each one. Or sorry, two to each one. This one has to split. Uh-oh. Now, that's a little tricky, but it's really pretty simple. And Jared figured out the game. There's a trick with this, and it's called the drop and swap. If we have these charges up here, we can always find the formula by taking the charge up top and taking it down and putting it over on the next one. Now, we don't ever put a negative or a positive sign. We just put the value. So the 3 comes down here. So we can do it that quick. We don't have to draw the dots. If I have aluminum oxide, I take Al and I look up here, and what's its charge? +3. I have oxygen. I put it here and I look up and its charge is a -2. So the formula, you just drop the numbers and swap their positions. So the 3 goes here, the 2 goes here. This would be the formula for aluminum oxide. Are we all right with that? Okay. On page, whatever we're on, try a couple on your own. So let's say you had sodium phosphide. I'm asking you to just find the numbers that go right here, like the formulas. If I had potassium oxide, how about that? And then aluminum nitride. Try these 3 and just write out their formulas. We're just looking for the numbers that would go here on each one of them. Now, one of them is a trick question. They would just cancel each other out. Good job, Ethan. You're welcome. Okay, check with your partner. I got Odessa covered.
I'm not done with the last one.
You're doing great so far. James, you doing all right? Yeah. Okay. Okay. So who had Na3P? Raise your hands. Uh-oh. Okay. Thank you. Na3P. We took them, we dropped them, we swapped them, never put the negative sign. Who had K2O? Raise your hands. All right, good. And then this is the trick one. It was Al +3 -3, which you would be tempted to put Al3N3, but if they're the same number, they just cancel each other out. Because try and remember, the whole reason we're doing this process is so that these numbers add to 0. Well, they already do. +3 -3 already add to 0, so I don't need these numbers. Now, these numbers that we put right here, these are called subscripts, and they're going to be really important for an activity like what we call naming and formula writing coming up. And then they're really, really important for the grand scheme of balancing and doing stoichiometry. Now, what's that? You missed it. You know you did. Don't even lie. Well, we're going to baby step it through. It'll be a piece of cake because you've already done it. Gabby was in AP for a little while, first try, and already learned to do stoic and loved it. It was a fun class. That doesn't, I don't know. That's kind of a, hated it, Davidson, but that's okay. All right. This works for any combination of metal and non-metal. Now, what we'll do is we'll actually take it from a name. So like it would say, what is the formula of lithium oxide? And then the fact that they are neutral, the fact that I can drop and swap them, I can find it pretty easy. I take the two metals, lithium is Li, oxide is O. I find the charge for lithium's a +1, oxide's a -2. Oxide and oxygen are the same. Oxide means it's paired with something instead of just the element. So it's Li2O. So we could go from a name to a formula. Okay. I have this video that we're going to show. It will wrap us up. So go ahead and pack your crap up. It's just kind of a deeper dive into ionic bonding.
I want to look at why.
He'll really draw it out in a way that helps you if you really do pay attention.
In order to really understand what's going on in ionic bonding, we have to take a look at the individual electrons that live.
So we did the boxes. It's the same idea. His picture's probably easier to follow though.
Also 11 electrons in the sodium. Okay, the same thing is true with chlorine. It has an atomic number of 17, 17 protons. It's starting out without a charge, so it has 17 protons and 17 electrons. Now, we can take one of these diagrams and fill it in from the center on out with a number of electrons. So, for sodium, that's going to look like this. 11 electrons arranged around the atom from the center out. And for chlorine, it's going to look like this. 17 electrons arranged around this from the center. Now, you may not be able to tell from these diagrams, but these are two very unhappy atoms. The reason why has to do with their valence shells. You remember what valence shells are? They are the furthest out energy level that still has electrons in it. Okay, so for example, this is the valence shell of sodium. It's got one electron here. And this is the valence shell, the furthest out shell for chlorine. Okay, the reason why these two atoms are so pissed off is because every atom wants to have a full valence shell.
What do we call that?
Every atom's goal in life. Sodium
What do we call that rule?
Because it only has one electron in its valence shell, and it has
The octet rule.
empty spots. Okay. Chlorine, on the other hand, is also upset because it's got a mostly full valence shell, but it's got one empty spot. It's so close. It's so close, but it's still super unhappy because the valence shell isn't full. So sodium and chlorine are both unhappy. They both want to fix their situation. And in trying to fix it, that is how they're going to end up with an ionic bond. Okay, so how are sodium and chlorine going to get happier? How are they going to fix their situation? How are they going to try to fill their valence shells? Well, take a look at this. They can help each other out, okay? Chlorine has one spot left before it's able to fill its valence shell. And so what happens is sodium can give chlorine one of its electrons, okay? So this electron moves from sodium to chlorine to fill this spot. Here's what we end up with. Okay, let me just show you what's going on here. Okay, so we got sodium, we got chlorine, and this electron up here moves between them. Okay, so it leaves sodium.
Oh, magic.
Chlorine. Okay, and now chlorine has filled this empty spot with one of sodium's electrons. Okay, so now chlorine is super happy. It has a full valence shell. It's achieved its goal in life. But take a look at sodium over here. Though you may not know it, sodium has also achieved its goal in life. Because when it gave this one electron, when it gave the electron to chlorine, it totally emptied out this valence shell. Now you might think, okay, that made it even worse because now it has 8 empty spots it has to fill. But here's the thing. If you can get rid of all of the electrons in your valence shell, it's like that valence shell just disappears. Sodium doesn't even have to worry about it anymore. Okay, so it gave away this last electron in its valence shell, and now it's like the valence shell
this guy
just disappears.
Kaboom.
Is now sodium's.
Or was it? It was bam. It happens or whatever, right?
It's totally full. So by giving away that one electron, it could get rid of its whole outer shell, and this is its new valence shell. It's full, and sodium is happy.
All right, that's actually pretty good timing of where to end. You guys are great. Goodbye, my friend. We'll see you after school. Adios, my friends. Hello.
Hey, Davidson,
Yes.
can I run this poster out to my car?
Sure. All right, you'll need an iPad. We have a little quiz today. Oh, dang it.